All right, so this lesson here is going to take a look at a strategy, actually a procedure for calculating something called an empirical formula. Now let's first very briefly talk about what this is. An empirical formula is the simplest reduced ratio version of an actual chemical formula. So the actual chemical formula for any kind of chemical compound is called its molecular formula, and the simplest reduced ratio is called the empirical formula. For example, this rocket fuel called hydrazine has a molecular formula of N2H2, but we notice that if we reduce these subscripts 2 and 2 by the value 2, meaning divide them by 2, it reduces to a simpler ratio of 1 to 1. 2 to 2 is the same ratio as 1 to 1. So this thing called the empirical formula is the reduced version, the simplest ratio of atoms or ions for any chemical. And for the sake of brevity or being brief, we're not really going to talk about the value of that right now at this moment. So if we look at C8H18 again, it looks like they have this 2 in common that would reduce to C4H9. So empirical formula, we're going to take a look at a strategy for calculating the simplest reduced version of a formula for any chemical substance if you are given the proper data. Now, the proper data would be what we call percent composition data. So if we have the percent composition data, what we look at is there's a strategy for doing it that makes it a little bit easier to remember. So I made up I didn't actually make it up, I stole this. You always steal good information from other instructors. So there's a little rhyme here. It sounds like this: percent to mass, mass to mole, divide by small, multiply till whole. And what we need to keep in mind is that last step might not necessarily be needed. So, if we had a little beatbox going, percent to mass, never mind, mass to mole, divide by small, multiply to a whole. So that is the steps that get us to think about, okay, how do we do this? So again, this is going to feel like what I would call mathematical gymnastics. I'm sorry that it is that way, but this strategy has some value in the practical world called chemistry, because really what it can do is it can take analytical data, like percentages of different chemicals, and it can predict what that chemical actually is. So if there's something in our air, our water, or our soil that maybe is a contaminant, and we need to know about, well, how bad is that contamination? We have methods for identifying what the actual chemical is that's contaminating our air, our water, or our soil. And it comes from very specific chemical analytical equipment, which we talked about briefly in class. Okay, so what we want to keep in mind is this step here that says divide by small. After we do that, we want to evaluate the value that we get and see, is that close enough to a whole number to accept it or not? And this is the criteria we're going to use. If it's within 1/10 of the next whole number, we're going to accept it. If not, then we're going to have to do something in the strategy. For example, 2.33, that's like almost 0.7 away. That's not 1/10, that's 0.7. It's 0.7 away from the whole number 3. It's 0.3 away from the whole number 2. So we can't accept that as a whole number. Now, if we look at 1.03, that is certainly within 1/10. There are 0/10. That's pretty much the whole number 1, right? 0.97, that's certainly within 1/10 of the whole number 1. 2.04, certainly within 1/10 of the whole number 2. This just gives you some kind of like rule of thumb to help you along a little bit. This isn't really etched in stone this way. 3.94, look at that's within 1/10 of the value 4. So we'll accept that as the whole number 4. All right, let's get down to business here. All right, so the rhyme sounds like this: percent to mass, mass to mole. So let's do it one step at a time. Percent to mass. all that really means is we're going to take these percentages up here in the words, 68.54% carbon, and we're just going to make them mass quantity. We're going to change them to grams. Change that to grams. Change that to grams. Now I could explain it, maybe I should, what we're really doing. What we're doing is we're assuming if we know what 100% of the compound is made out of, we know the percentages, then we're assuming like we have 100 grams of the chemical. And if we had 100 grams of the chemical, 68.54 of them would be carbon in this case, 8.63 would be hydrogen, 22.83 grams would be oxygen. So percent to mass. So all we're going to do is change that percentage sign for carbon to grams. Right, so there it is. And then we're going to do the same thing from hydrogen to grams. And then we're going to do the same thing from oxygen to grams. So they came right from the numerical amounts in the words, percent to mass. The next step, mass to mole. Now we've spent a fair amount of time doing what we call quantity conversion. And anytime that you want to take a mass quantity and make a mole quantity out, because the second step is mass to mole in the rhyme, we use what's called the molar mass. The molar mass of any element is listed on the periodic table next to that particular element. Let me pause the video here and just go grab a copy of a periodic table for the sake of time. Guess who's back? Yes, I'm back. Okay, so we got a periodic table, and listed on the periodic table would be the masses. For example, if you're looking at lithium there, 6.94, that's the molar mass for lithium. Hydrogen, 1.01, that's the molar mass for hydrogen. So we're going to list, we're going to use the molar mass for each chemical element to convert mass to mole. Again, percent to mass, we've already done that. The percentages are now gram amounts. Mass to mole. What we're going to do is we're going to create mole amounts. So here we go. 1 mole of carbon is the same thing as 12.01 grams. So really all that means we're doing, if you were using that dimensional analysis strategy in class, 68.54 gets divided by 12.01. Now, if you wish to just divide it because you know, to turn a mass into mole amount, I just divide by the molar mass, go right ahead and do that. So you don't got to make it look like the fraction here. What you do have to realize is you're going to divide the mass by the molar mass of the chemical. And for carbon, just so you know I didn't make it up, right? The element carbon, I can't see my video here. If we're looking for the element carbon, there we go, it's 12.01 grams, right? So that would be the molar mass. We divide 68.54 by 12.01, we get 5.707. Percent to mass, mass to mole. Let's do the same thing for hydrogen. Molar mass for hydrogen is 1.01 grams. Divide 8.63 by 1.01, you get 8.545 mole. Do the same thing for oxygen, right? Again, they're coming off the periodic table. I'm not making them up. Oxygen would be over here. Kind of hard for me to see what's going on here. Let me see if I can do that better. There we go. Oxygen is 16. Okay. So the molar mass for oxygen, divide 22.83 by 16, 1.427. Percent to mass, mass to mole. Next part of the rhyme, divide by small. So of all these numbers, which one of these is the smallest? Well, of course, it's 1.427, right? So we're going to divide each of them by 1.427. Seems kind of random. It's really not. What we're trying to do is create whole numbers. You're going to be guaranteed to create the whole number 1 if you divide one of these by the exact quantity of it. So I'm going to divide each of them by the smallest. Divide by small, 1.427. I get the value 3.99. Let's look at that. Is that within 1/10 of the whole number 4? Of course it is. We'll accept it as 4 then. Let's do the same thing with hydrogen. Divide by 1.4. Oh, look at that, 5.988. Is that within 1/10 of the whole number 6? Yes, of course it is. Let's accept it as 6 then. And then lastly, 1.427, well, we divide that by itself because divide by small, right? It makes the whole number 1. Of course, that's within 1/10. That is 1. What we got is we ended up with whole numbers. We got a whole number 4, a whole number 6, and a whole number 1. And that becomes the quantity ratio that we put together to make what we call the empirical formula, the simplest reduced ratio. So this last step in the rhyme is not necessary, and we're not going to use it. We are not going to multiply till whole. So we'll cross that out. We won't use that portion. So we write a formula. If we look here, carbon requires 4, hydrogen requires 6, and oxygen requires 1. 4, 6, 1, the empirical formula. There it is, the simplest reduced ratio. Now, this might take, this chemical analysis might, from this data up here, might take down the possible 60 million chemicals that this unknown thing could possibly be and reduce it to just 2 or 3 choices now. And then there would be other strategies for determining, is this nicotine? Is it codeine? Is it caffeine? Is it THC? What is it? So maybe it's something in our urine, our blood, our food. Okay, let's move forward. Second example, percent to mass, mass to mole, divide by small, multiply till whole. So again, I'm not making it up. Let's show you where that is. You have access to these notes, right? So the rhyme, percent to mass, mass to mole, divide by small, multiply till whole. There it is. Okay, the first example we demonstrated, that was it. We ended up with a chemical formula. When we're done, the simplest reduced ratio, a 4 to 6 to 1 ratio. So let's go back. Percent to mass. We're going to take these percentages in the words and just change them to gram amount. So it's no longer percent, no longer percent, no longer percent. Keep the numbers, but now they're grams. Carbon, hydrogen, oxygen. Mass to mole, right? We use the molar mass for each chemical, right? Molar mass for carbon, 12.01 grams, right? That actually means all we're doing is we're going to take 17.96, and we do this by division, divide by 12.01, and we get the mole amount of carbon. So there it is, 1.495. We're going to do the same thing for hydrogen, different molar mass, right? 2.267. Do the same thing for chlorine, different molar mass because it's a different element. 2.250. Percent to mass, mass to mole. Next step, divide by small. Well, of all of these, the first one, 1.495 is the smallest. So we'll divide each of them by that. Of course, 1.495 divided by 1.495 is a whole number. It's the whole number 1. Next example, right? 2.267 for hydrogen, divide by small. 1, oh, look at that, folks. That is not within 1/10 of the whole number 2. That is 5/10 away from 2 or 5/10 away from 1. That is not a whole number. We're not going to accept that. Let's move on to the next one. Again, not within 1/10 of a whole number. We're not going to accept that. So percent to mass, mass to mole, divide by small, final step, multiply till whole. So I'm thinking, is there some number that I could multiply this by that would create something that is within 1/10 of a whole number or so close to a whole number that I can accept it? So my suggestion is start with easy numbers. Don't start with 1. If you multiply by 1, nothing's going to change. So start with 2, right? So we'll multiply by 2, right? Let's see what happens. Whoops, didn't mean to do that twice. 3, oh, look at that. That's within 1/10 of the whole number 3. I'm going to accept that as the value 3. 1.505. Right? If I multiplied this one by 2, then all the other ones are going to need to be multiplied by 2. So the one on the bottom, I multiply by 2. I get, oh, that's within 1/10. We'll accept that as the value 3. And then the top one, I'm going to have to multiply by 2. And we get 3 whole numbers now that we can use to write our formula, 2 to 3 to 3 ratio, and we relate it to the elements. Carbon, I would need 2. Hydrogen, I would need 3. Chlorine, I would need 3. And our empirical formula is going to look C2H3Cl3. Percent to mass, mass to mole, divide by small, in this case, multiply till whole. Won't always be used, that last step. But in this case, since these numbers right here were not within 1/10 of a whole number, we had to multiply by some value to create a whole number. Start with simple numbers 2. If 2 doesn't work, move to 3. If 3 doesn't work, move to 4. Probably about 90% of the time, 2 or 3 work. Okay, percent to mass. We're going to do it real quickly now. Change the percentages to gram amounts, right? Look on the periodic table for the molar mass. Divide the quantity 4.75 by 12.01. You'll get 0.396. Do the same thing for hydrogen, 0.4 divide by 1.0. Oh, look at that. You get 0.396 again. Do the same thing for bromine. Bromine's much heavier than either carbon or hydrogen. This is a typo here. This should say bromine. Brewer, what are we doing? I have to copy or, amend that in the actual file, which we'll do later. Okay, so bromine will divide by 79.9, the molar mass for bromine. Percent to mass, mass to mole. Divide by small. Next step. Well, 0.396 is the smallest of those 3 values, so all of them are going to be divided by that. No problem there, right? 1 is well within 1 of a whole number. It is 1, right? So this, when I divide the second one, we also get 1, right? Well within, that is the whole number 1. Lastly, we get to, is that within 1/10 of the next whole number called 3? Of course it is. It's 0.1 away to go from 2.9 to 3, but look, that's even closer than that. So we're going to accept that as the whole number 3, and we're not going to have to worry about multiply till whole. We have 3 whole numbers already that we can accept. So the ratio, 1 carbon, 1 hydrogen, 3 bromine, and that's how we deal with what we call empirical formula. I know it feels like it is mathematical gymnastics, and it probably is, but it's a nice shortcut to help you sort of remember. It's really not a shortcut. It's a way to remember the strategy to do it. So until the next time, I hope you found this useful, and I'll be providing more resources to support you as our time progresses.